So I'm going to do a little bit of talking here today about some of our thoughts or previous thoughts that I've had about how to handle induced earthquakes, specifically coming at it from a risk-informed perspective. Um, Please, as Chris said, feel free to interrupt if you have any questions along the way. It essentially means that I'm not explaining something clearly, which happens all the time because I forget details. So yeah, don't be shy to interrupt. Oh, why is this not advancing now? There we go. Okay. So first piece here, I'm going to break this talk into two parts here. So first talking about thinking about earthquakes in terms of statistical bounds on how they might stop, or getting a grasp on this concept of trailing seismicity and quantifying some of these pieces a little bit better. Part of the reason why is just induced earthquakes in general have been numerous and growing worldwide recently. Often these have been large enough to be felt, so causing concern amongst people and anxiety. As well, some have been large enough to produce these mid-magnitude 5 events that have been, in some cases, causing economic or even human losses. So that's one end, one extreme end where you can have these risks that are actualizing, but on the other end of the spectrum too, there's been overreactions in the sense that moratoriums have been placed on resource development, sometimes in part or entirely due to concerns around induced seismicity. So just for a motivation piece, there's this clear need for an effective and transparent management of this problem. And a lot of this first part of this, I'm putting maybe a little bit of the cart before the horse here by talking about this, but we've come up with an approach where we do this in a risk-based way to figure out what red light should be, and we can do this so it changes spatially. Part of this requires knowledge about trailing seismicity is one of the key pieces. So this is again, a motivating factor in something like that. And not only is trailing seismicity important part, but it's actually the most important part. So doing just quick sensitivity tests on this type of analysis, where you define red lights in a risk-informed way, shows that trailing seismicity in terms of the nuisance that can come out of it, as well as the damage, is going to be the most important factor to constrain and understand. So having a sense of what's going to happen after you turn off the pumps is going to be extremely important, even more important than something like the perturbation or error uncertainty factor and something like a ground motion prediction equation. So this has kind of motivated this one piece of this talk to get a better sense of what trailing seismicity looks like, or even how we can put some sort of statistical bound or modeling on this. And then last for motivation pieces here is looking at some of these exceptional cases. So here's a couple cherry-picked cases where I've showed something where induced seismicity isn't going exactly the way we anticipated. So there's a case from the Duvernay, Alberta, where a magnitude 4 earthquake happened. And essentially, as the sequence was growing in magnitude, it went from sub-magnitude 2 to above magnitude 4, with nothing in between that. Pohang, we had magnitude 5.5 event that occurred 2 months after shut-in of the well, and as well Preston New Roads fracking case in the UK. The largest event here happened 60 hours after the completion of the last stage that occurred in this. So trailing seismicity from an anecdotal point of view here, or in these cases, can be a very significant factor, and that backs up some of the stuff that I've been saying here previously. So if we're motivated then to answer this question about how does induced seismicity stop, we can maybe back up and start thinking about other questions related to how do tectonic events stop, and maybe adapt some of these concepts, or at least use this as a guiding principle. So the first part of this is we looked at something like Both's law. So essentially, this is just saying that if you look at the main shock and the aftershock, the difference in magnitude between these two tends to be about 1.2 magnitude units. Technically, I guess not a law, more of an empirical observation. But this has more recently been understood as a probabilistic consequence of two more fundamental observations. So if you take something like an Amori decay, which can get you the rate of events, but also then the total number of events based on these parameters, which have typical or reasonable bounds on what they can be, as well as something like the Gutenberg-Richter magnitude frequency distribution, which also then says something about the proportion to big to small earthquakes. If you combine these, you can get a relationship like I'm showing here, which essentially says that that difference in magnitude has something to do with the population ratios between the total number of events and the number of aftershocks. And if you combine these concepts with the typical ranges of what these values can be, what nicely drops out of this is the magnitude difference of the 1.2 here. So we're going to start with this and adapting something like this and exploring how it works or doesn't work for induced seismicity. So for deriving something like that, we can look at the sample size hypothesis that Van der Elst did, linking the maximum or largest magnitude of an earthquake in a sequence to the population size itself, just shown by this relationship here. And if we take that and split that into two different distributions, one population that's occurring during stimulation and another population that occurs as the trailing piece afterwards, then we can combine these two relationships just by taking a difference, essentially, showing that this has something to do with the ratio of earthquakes that are going to occur in each of these bins, as well as this variability piece that's just going to give the shape of the distribution. So that's what's shown in these plots here, is this upper equation shown here, and the lower one shown here. So depending on how you skew this ratio, the magnitude difference between the difference between the largest magnitude and the trailing, or the stimulation sample, will skew either way, depending on what that ratio is. And then you intrinsically always just have this uncertainty or error related to this piece in here. So this itself here gives us a sense to forecast or predict what we think this delta M between these two would be, given some sort of known ratio of what we think that RS is going to be, or that ratio between the stimulation and total number of events. So this is going to have some assumptions behind it. So we're assuming already that this is going to be a point process, which, if I'm trying to justify these things, typically works in tectonic settings. We're also going to be assuming that this is identically distributed based on the Gutenberg-Richter, and then we're having this sample size hypothesis. Lots of cases, this is actually observed empirically. And then we're also going to assume not necessarily what model, but that there's going to be some sort of a decay, which again, after you turn off the pumps. But maybe a bit more than trying to convince you that these sort of assumptions are supposed to apply to the data, the best thing that we can do is actually just check or test this against real data and real cases. So that's what we did for this particular idea here, is we looked at cases around the world where they had clear operational endpoints. So fracking, geothermal, hydrothermal disposal cases where they had turned off the pumps. And this gives us some 80 cases worldwide where they also had some sort of information, either on-off time or actual rates of injection, to get a sense of when these operations were occurring, so we could bin them into the two portions. And I'm just showing essentially globally where some of these cases, as well as sorting out which cases were used in these particular, for this particular data set. Just showing here a simple idea of what's done in something like this to test this idea is looking at, first of all, you bin this based on when injections are occurring. So yes, earthquakes binned in the blue set, essentially showing, and then you can grab from that the number of earthquakes that occurred above the magnitude of completeness, as well as the largest magnitude earthquake in that, as well as all of the earthquakes that occurred outside of that time, so trailing events, and the largest magnitude in that data set. And then this can be repeated essentially for every single one of those cases. Very simply here then, what we're looking at is something like, we have those two for each case, the difference in magnitude. So the magnitude of the trailing event minus the largest stimulation event, shown on the y-axis here, and that relationship that I had shown previously on the x-axis with this. And what we see out of something like this is a very nice correspondence to what we would expect. So the expected relationship being shown just by the solid black line, and the fitted relationship being shown by the dashed black line in this case. So just doing a simple weighted regression nicely corresponds to that. We can also, though, you also notice maybe that there's significant scatter in this relationship. So the smaller dashed lines here are showing the 95 and 5% percentiles of this data set. We can also then try to check to see if the residuals, this distribution, actually nicely correspond to this distribution as well, or what we would anticipate from this piece of the equation. So that's just what's shown here in this plot. If you take everything for the measured parameters on the left side of this, we expect that that distribution should look like this equation here. So just two random variables, the logs of them, and the natural log 10 of that, which produces the black line for the PDF, or the black line here for the CDF of this distribution. And what we see is that essentially doing something like a KS test, so a statistical hypothesis test to answer the question, are these two distributions different? We can't we can't assert that essentially. So the null hypothesis that they are drawn from the same distribution is what's kept here for something like this. And this is similar if we do bootstrapping or resampling of this data set.
Ryan, quick question. It's Chris. In the slide before this, you mentioned that you were going to fit a line and you were going to do some kind of weighted fit. What was the weighting for? What did you have more confidence in certain things?
Yes, absolutely. So we had done it a couple ways. Most of the weighting was done by the number of samples in each of these cases. So if you have a 1,000,000 sample catalog versus another catalog that had 10 events in it or something like that, then you weighted it based on the square root of the size of it. But we had also, I kind of just tucked this underneath the rug here, but there was different grades of data as well. So A being they actually had like high quality catalog data as well as injection. This being just if the data was on or off for the operation. And then this is where I had to literally pull something off of a paper, essentially, where I had to put it into like a picture editor and pull that kind of information. So we also tried that. It didn't really make a big difference, essentially, though. But yeah, thank you for the question.
Yep, thanks.
What was I saying? Okay, right. So these two things, we can't reject that they're different from each other. So up to this point, this nicely says that this actually has some sort of predictive power in doing something like this. But if you're maybe being a bit, you're grilling me a bit on something like this, you may say, okay, cool, I believe that understanding something about what this delta M could be trailing would be important. But you've essentially just changed the goalpost. Instead of knowing something about delta M, now you need to know something about this ratio instead. And maybe we actually haven't learned anything yet. So continuing to examine a little bit more about the statistics first, just empirically speaking of what this population ratio looks like, as we see a highly skewed distribution of what that stimulation ratio is. So almost all of the cases have something like 90% of their, or 80 to 90% of their earthquakes occurring during the stimulation phase with only a small portion of it trailing afterwards. If we assume that these things are just going to be, have some sort of random piece to them, this is the distribution that we would expect for those two population accounts, which is significantly different than the actual observed piece of it. So this is saying, or we can infer that something is going on here different from just random sampling of this. And we've provided then also a beta distribution fit to this distribution of R, that RS, so that you could use something in a sense to forecast this. So you can draw from the distribution of RS and then use this equation to get a sense of what that delta M could be for an operation based on global averages of what this looks like, essentially, for all of the cases out there. This is good, I guess, in the sense that also a lot of the cases have observed this. So I know from seismicity in the Duvernay, almost 90% of the earthquakes tend to be occurring during the stimulation phases, as well as another case where they had done an ETOS fit to some seismicity in China, where some of when including a forcing term in the ETOS model, essentially 90% of the earthquakes fell under this forced term, with the remaining 10% being some sort of other type of earthquake, like these decaying sequences. So maybe just to get a simple sense of what's going on or learn a little bit more about what this means, essentially, is looking at the simplest archetype of what could be happening with induced seismicity. So as you stimulate, you inject at a certain rate. You do this for a period of time, TS, until you turn that piece off. The earthquakes start in a lagged interval after that, and then decay with some sort of decaying shape to it. So some sort of aftershock like shut-in decay during this period. If you take something like that, so we use a model where the number of events during stimulation is proportional to the volume that's put in. So like the Shapiro kinds of relationships here, as well as I'm just going to start, we worked on this further, but using something like an exponential model where it's just decaying with some sort of mean decay time parameter. If you make these assumptions and also that the induced seismicity rate starts at that and begins to decay, then the ratio where you would expect that the population count ratio between the number of trailing events and stimulation events should have something to do with this lag time, the mean decay time of that exponential distribution, as well as the total stimulation time. And if we even just put in typical parameters that are something like for a frac operation, for some of these, we get something like the RS value being something on the order of 82%. But this isn't necessarily to say that this is a full, actually physically meaningful model. This is just to learn something about this, about what pieces or what things would be constrainable or important to know more about. So the next thing that we did is actually take that, if we assume that actually holds, do a Markov chain Monte Carlo approach to maximize the likelihood to the empirical RS distribution, to instead of just getting fixed values for what these delta T and mean decay parameter are, get what the distribution would look like in order to satisfy the empirically observed distribution of RS. And essentially what we see in these cases is that many of the cases have values that are going to be less risky or less likely to encounter big jumps in trailing seismicity, but you have these large tails that occur afterwards, suggesting that we have sort of like these black swan events where lots of cases don't encounter something significant from trailing seismicity, but every now and then you get cases that are going to be like this because of this distribution. So if that's the case, and that these sort of mean decay parameters, as well as the delta T, the lag times, are going to be important to understanding what trailing seismicity is, then one of the most pragmatic things to do would be to measure them in situ rather than trying to guess ahead of time. So this brings up the idea that we're proposing is to build something like a seismogenic fault injection test, or SFIT. Doing this in terms of like an analogy to DFIT. Reservoir engineers, when they're going to do something like do a frac operation, they will do a DFIT, which is a diagnostic fracture injection test, and are also known as a mini frac. And essentially what they're doing here is they're taking a small fracturing process to learn something about the reservoir ahead of time. So when they do their big frac, they know a little bit better about how it's going to respond. Very similarly, you could do something like this to measure some of these parameters. So what is the proportion of events going to be, or what are some of these decay parameters going to look like in terms of that trailing seismicity piece? And we could do this even then in the sense of repeating this test, multiple on-off cycles to get better constraints on that, or to see if there's any sort of hysteresis in this. Some of the things that would come out of this based on just this model so far is doing this in non-periodic repeating, or doing this non-periodically. So don't have the exact same interval between this. And possibly also not at all predicted from this model is to chirp through injection rates. So having various injection rates to see if there's any influence from injection parameter on, or the injection rate on that as well, would be very cool. This is one of the newer pieces. So this is where we had applied this sort of approach to figure out what the red light should be for the Preston New Road case. What was very interesting about this case here is that this, for each subsequent stage of stimulation at this well, is the ratio of trailing events or the ratio of stimulation events, sorry, kept monotonically was decreasing with each subsequent stage, and each stage was also becoming more risky in terms of the amount of trailing seismicity that was occurring until they essentially had this larger event. And this is, again, getting ahead of myself because I haven't presented any of the methods here for the next piece. But what we essentially seen in this is that if you had adapted to include this change of new information, then it potentially would have suggested that we should have stopped at this stage 6, and preventing essentially this larger event from happening at stage 7. So for this first half of what I'm going to talk about here, I've looked at a statistical concept to figure out how or what the bounds on trailing seismicity could look like for induced seismicity. This seems to work reasonably well for this, knowing something about the RS or that stimulation ratio. But even better than that would be to essentially measure this then in situ to get these parameters ahead of time to get a better sense of how you might de-risk an operation in the future. Actually, with this, I'm happy to chat briefly if anyone had any questions about this piece. No, none.
I've got a question, Ryan.
Yeah, okay.
So you just showed us this case here where there are multiple stimulation phases, and you said, well, there's this big one that wouldn't have happened if we'd stopped at 6. But
Yeah.
is that a certainty? Like, given the possibility of aftershocks, isn't there still some possibility that it could have happened from 6? It wasn't really directly stimulated from 7.
Yeah, no, that's absolutely fair. So this is in this case we have the power of hindsight, of course. So this is making all sorts of assumptions. It's assuming that each stage has some sort of causal connection with the next or the previous one, which doesn't necessarily always have to hold in real life. So it's not clear how you would link discrete stages to each other. But in this particular case, it's suggestive that something interesting is happening here. Because each case, this RS value is going down and it's going down significantly.
Yes.
And in each case, then the amount of trailing seismicity and the magnitude differences are growing. And so we had first done this red line here is if you assumed the global average for the trailing seismicity and you do this second half of what I'm going to talk about, you can figure out that the red light should have been this solid line. But if you updated using these new values of what the trailing seismicity actually was in measurement, then it changes to these smaller values with time. So it's basically just a way that you could adjust to real-time information in an ad hoc way. So no more thought needs to be put into how you would do this, let's say professionally, or more seriously think about this problem. But it's at least enough to say that there's something interesting going on here to build on this idea.
Yeah, well, it's certainly a practical problem, isn't it?
Yeah, yeah. I mean, so that's also why doing the SFIT kind of test makes the most sense, is actually test in real, either in situ or lab conditions, if this even makes sense to do, or if it's, yeah, workable.
Gotcha. Thank you.
Yeah. Okay, maybe I'll move on to the second piece. So the second part of what I wanted to talk about is then taking this approach, or at least this trailing seismicity part, and putting it to work in a real life case here, or at least a prospective case. So the Netherlands is interested in developing geothermal energy. So there's always this growing need for new energy, and with climate change on the horizon, as well as the IPCC's 1.5 target, there's also this need to be a bit more selective about the energy sources that are being picked. So we want to reduce our carbon footprint while also still meeting these sort of energy security and energy independence needs. So geothermal is a prospective idea that could be used in the Netherlands. One such well that's come up is the California well. So just generally speaking, a lot of the thoughts on wells are going to be sedimentary, so these like low enthalpy or hydrothermal systems. But some of the deeper systems in the Dynantian carbonates are targeting these sort of faulted, fractured, or karsted regions, because as you go deeper, obviously, access to this sort of permeability changes. So having this enhances the flow and potential for geothermal, but also typically then can be associated with earthquakes. Or if you're thinking about something like an enhanced geothermal system, that's also associated with earthquakes. And I'm just showing here for context some information for the Netherlands here as to where some of the natural seismicity and also the Groningen seismicity is occurring, as well as some of these dinancian carbonates shown here in the blue as potential target areas for this kind of deeper geothermal or maybe even EGS type of operations. So that California well has already also encountered induced seismicity in the Netherlands. So there's this sort of clear need to better understand the earthquakes. In some of the stuff that I've said previously motivating, we already have the 5.5 Pohang case that's caused both economic and human losses. The Basel event, which ended EGS or ended the EGS operation in Switzerland. And like I just mentioned here, this 1.7 event that just happened in the Netherlands. This is also not happening in a vacuum in the Netherlands either. So there's the previous history of the Groningen earthquakes related to gas production in the Rontelegend group, with the largest event being this Huizinga event, magnitude 3.6 event. And essentially because of the public outrage around this event, the Netherlands have decided to abandon this resource. So they're going to strand some 800 billion cubic meters of gas or billions of dollars worth of gas in the ground entirely because of worries or concerns around these earthquakes. So there's again a clear need to transparently manage this problem, this time in a forward-thinking way for EGS. So typically how EGS operations, or how induced seismicity, I should say, operations are managed is through something like a traffic light protocol. Essentially what they're going to be doing is the philosophy that I'm going to be thinking around in this is in the green light period, the operator is allowed to proceed as they see fit. As magnitudes grow into something like this yellow light territory, then the operator has to enact some sort of mitigation strategy, some sort of magic to make sure that the earthquake magnitudes don't continue to grow until you reach the red light, which is going to be essentially the last possible stopping point. So an endpoint where some sort of regulatory intervention happens and the operation is shut down. Not every single traffic light protocol adheres to this kind of philosophy, but most of them do. So this is going to be the one that I'm going to think around. So this immediately brings up the first question then is, what is the best threshold to set then for something like a red light magnitude? Or maybe building on that, or how will you even do something like that? So in building on that or some of the previous work, we looked at how you would do this in a probabilistic sense, using a risk-informed approach, as well incorporating some of the pieces that encounters this ability to capture trailing seismicity. So what's going to happen after you shut in the well. In this sense, then you can get an idea of what sort of magnitude, if you pick a red light, what sort of magnitude scenarios are going to happen after the fact for the largest events. Then we can also look at risk metrics, so something like nuisance or damage. And I'm just showing some previous work that we had done this in a simple zero-dimensional approach, but we've since built on this to actually incorporate, let's say, mapped information over a broad region. So the workflow for parts of how this type of work goes or moves forward is you have some sort of information on the depth or the boundaries of where operators are going to be considering doing their operations that could cause earthquakes. And you also previously from the talk, for the first half of this talk, we have a sense of what trailing seismicity can look like. Together, we can combine these pieces to get a sense of, if you know where the operation is going to be, you have a sense of where and how big the earthquakes could be. If you also then combine regional information for ground motion prediction equations or site amplification, you can also translate that into some sort of ground motion or hazard scenario for the amount of ground shaking you might anticipate from those earthquakes. We can also pull in exposure information from population density, so just essentially where people are located at, And we can also combine different types of fragility functions, so a nuisance function, a fragility function, or a vulnerability function, to translate that exposure and hazard piece into nuisance impacts, so how many people felt it, damage impacts, how many homes were damaged, or LPR, local personal risk, which is the individual's chance of fatality for building collapse. Just repeating this again, going over it in a bit, because it's a bit it's a bit convoluted. So you have some sort of assumed operation location. You're going to use a trailing seismicity piece here to get a sense of after a red light event is triggered and the trailing events occur, what was the largest magnitude that occurred in that population set. You also have from information on the geological subsurface, essentially, what sort of geothermal gradient is going to be in the area, and you can pick some sort of isotherm to get a sense of what the depth of the operation would be to have to target to get economic viability out of the project. So this gives you essentially depth, and usually these earthquakes tend to occur near stimulation intervals for induced seismicity, or deeper in a lot of cases. So we have some sort of a perturbation around that. Then you can build ground motion scenarios from that, where we have essentially just this shaking as a function of space, which we also know population density is a function of space. So we can combine with previously calibrated, for example, nuisance function to get a sense of what is the chance of this event being felt at this location given this ground shaking. And if we know that, we also know how many people felt it at this, and we can just sum up over the area. We're going to look at not just earthquakes being felt in the yes-no sense, which is this CDI2 threshold, but also higher degrees of it being felt. So this is community dense decimal intensity. So 2 being the just felt threshold, 3 in terms of the subjective criteria from the did you feel it questionnaires being related to an exciting amount of felt threshold, and these other ones being degrees of frightening amounts of ground shaking. So we can quantify or stratify that into these different degrees, as well as something like the damage state being either just structure or non-structural cosmetic damages up to complete collapse. If we combine these pieces, we can get something that I'm just going to call a risk curve over here, which is essentially the amount of impact as a function of the magnitude, or the red light magnitude specifically. And then this is then also done in a Monte Carlo perturbation where we can get the full distribution of what this looks like. And for simplicity, I'm just going to be talking about or looking at the median values of something like these curves when we do this sort of estimation moving forwards. Some of the data that went into this for this particular study was, again, using geothermal gradient information that had been collected and sampled for all of the Netherlands, and assuming at 120 degrees isotherm, using slope-based proxies for VS30 to get the site amplification piece, as well as regional GMPEs, mostly regional or local fragility functions and vulnerability functions, although the nuisance function was pulled from North American data, as well as essentially land scan information of where all of the population are occurring, shown here for the VS30 depth and population information for the Netherlands. So the first way we can think about something like this is if we do this sort of isomagnitude approach, where for any given location, you essentially just say that the red light should be some sort of constant value. For example, red light of 3.0 or something like that, just for argument's sake. What we see if you do something like this is you get these spatially heterogeneous risks that are coming out of something like this. And if you notice too that this is going to nicely correlate with the distribution of the population. So essentially this is just saying that in highly exposed areas are going to be your most risky areas in terms of these aggregate metrics, like the amount of people that are going to feel it. And we can quantify how much that's going to change if we went to a less exposed region. Between these two, the nuisance and the damage maps, nuisance, they both change spatially and they both correlate with that population density, but it's going to be on a different wavelength or a different footprint, where it's going to be larger for something like a nuisance, essentially just because these moderate magnitude earthquakes of around magnitude 3 For the number of people that feel it, it's going to be on the order of hundreds of kilometers away from the epicenter versus tens of kilometers away for something like damage. Something like local personal risk doesn't correlate quite as well as with the population density. And the reason for something like that is because this is a local metric. So it's just the chance of this risk occurring for the person who's closest. And for the scenario of the Netherlands, essentially, there's people everywhere in every single one of these locations. So it mostly correlates then with the depth piece on this. So that's one way to think about it, looking at this from an ISO magnitude, and certainly lots of jurisdictions have done that. They have just selected a single threshold, but you might argue that this isn't quite as fair because your amount of exposure is going to change with the location as well. From that perspective, so if you design for something like in the most populous areas, then even as an operator moves out to these less exposed areas, then they might have to over design essentially for the amount of risk in these regions. A different way to look at this, or potentially a fairer way to look at this, is instead of saying a single magnitude of earthquake that you would stop at, is look at a single or agree on some sort of risk that you're not willing to exceed, and then use this approach to work backwards to figure out when you need to stop to make sure you're honoring this tolerance to risk that you'll choose. So this is just essentially an alternative way to look at something like that. This comes with, I guess, let's say the baggage, but also the benefit of then needing to pick what your tolerance to risk is. I say baggage in the sense because this is now additional work, but also the advantage in the sense because this makes it clear and transparent to people as to what sorts of risks are going to be taken when you're proceeding with this operation. So this is, I think, a significant piece for communication with local stakeholders. To essentially maybe even get them on board for operations. So there's going to be questions about types of risk. So what types of risks should be considered? My thoughts so far around this have been related to nuisance, damage, and local personal risk. Choosing those tolerances for each of these is going to have different degrees of nuance or difficulty behind something like them. So for the easiest case, local personal risk, this has already been put into Dutch law as to what they need to consider for earthquake risks, which is 10 to the -5 per year. So this is based on health standards and also the committee that came out of the Groningen. If we're going to something a little less concrete, damage is another risk to consider. We could take an approach where we just want to avoid damage, or maybe we want to do some sort of balance between the amount of expected loss of money from the earthquakes that were caused versus something like the expected cost of losing an operation. Those are options. Something like nuisance is far more nebulous, and there's less information about standards out there on how you would choose something like this. But we can consider something like previously available information. So maybe we want to take a bureaucratic approach and be consistent with a jurisdiction's standards for blasting or construction vibrations or something like that. Those are possible ways to do this, but I am an empirical seismologist, so I'd much rather do something empirical with trying to answer this kind of question. So what we did in this particular case is we took a whole series of earthquakes, but I'm just going to show you two here. We took the 2012 Huizinga event. So this was an event that spurred on the end of operations in the Groningen, and we compare it to the 1997 Roswinkel event, which was the second most impactful earthquake by our estimates. And we use these to essentially bookend what is happening. So for the number of people that felt this, at the CDI2 threshold for the housing event are given by the red distribution, and the Roswinkel event from the green distribution. And what we're essentially arguing here is that it has to be somewhere, the Dutch tolerance for risks probably have to be somewhere between these two values. And so we look at this distribution between these two and then take the P10 of that distribution as a tolerance. So this is at least some sort of way to get some sort of an estimate or a measure of what we think those tolerances are to have some sort of constraint on this. And we can repeat this not just for one metric, but different degrees of nuisance as well as damage and something like this. So the next question then is, if you have these tolerances to risk and a workflow to translate magnitudes to these risks tolerances, how do you then combine all of these different pieces? What we've taken is the simplest approach. So you just build essentially separate maps where this would be the red light value that you would need to stop at to honor this tolerance that we inferred. And then just combine them by looking at each individual point and taking the smallest value amongst these maps. And so that's what's shown here as this combination map, where the controlling factor is just then again plotted here on the right to show which piece is more or less important for the degree of nuisance. We can also do that then for multiple different risk types. So building something like that combination ISO nuisance map that I just showed, but also for damage and also for the local personal risk of fatality, and combine these three pieces into something like this. And essentially what we see is that something like that, the nuisance pieces and the damage pieces are going to be more significant. And again, changing on that different wavelength or footprint size for that, but then not as, these are going to be more risky concerns as compared to the fatality risk, which is essentially shown by this plot here where we've combined all of these maps. So most of the country, these sort of nuisance concerns are going to be the first concerns that you bump into, versus some of the northern parts of the country, more the damage risks are going to be some of the first concerns that you'll bump into rather than the nuisance pieces. Some of the last parts I just wanted to talk about here is maybe some justifications for these metrics and tolerances. So what we've done here is taken a spectrum of risks. In my opinion, that's good because you're going to cover a lot of different bases, both in terms of taking local risks like the fatality for an individual and moving into something slightly more aggregate or at like a portfolio scale, like housing damage, or even then moving into something at a further level, like just the amount of nuisance or how many people have felt that being the most aggregate version of this. In repeating this approach for a whole series of different locations, either inferring implicit risks that were taken for nuisance in different jurisdictions from their TLPs, or doing the same sort of bookending. There's different degrees or different tolerances to risk that have been taken for different locations, but each province or each discrete jurisdictions, when they do have multiple TLPs or multiple ways we can infer this, they've been taking consistent risks in each of these individual cases. So this is kind of interesting to see this, first of all, but then also how you could use this to essentially build in any of these regions like a third traffic light protocol that would be informed or consistent with the previous ones as well. And not only that, but then the Groningen risks that we had inferred are very consistent with some of the North American risks, risk tolerances, which going in ahead of time wasn't exactly what I would have expected. If I'm being a bit harsh on this as well, so this bookending approach does make an implicit assumption that there's some sort of single change point in people's attitudes, like you just pass a certain amount of number of people that feel this, and then this will spur on some sort of social change. That might not be the case. It could be some sort of cumulative piece to it, or maybe some sort of time dependence piece to this problem as well. But right now, there's not really any data to dive deeper into answering something like this. And this is also getting quite close to social science stuff. So maybe there's something that people can say from those domains to help build on how this sort of problem works a little bit better, to incorporate this in a more nuanced way. The last piece I wanted to talk about then is we can take this operation and make some sort of hypothetical operation. So let's say we're going to put an EGS operation right on top of the housing earthquake's epicenter, and see what would have happened, something like this. So these are these risk curves, the blue ones for the different types of, or different degrees of nuisance risks, the orange ones for the damage risks, and then the LPR risk shown in the green here. Each of them had been normalized to their normalized to their tolerance, so that this crossing at the 1 value is essentially the magnitude that would be the red light and inferred from that type of risk. One of the first things to point out with something like this is the Roswinkel and Hausinga event are somewhere around this roughly 3.5 mark. But despite the tolerances being inferred from these two events for both nuisance and damage, the approach requires it steps back a certain distance, almost a full magnitude from these earthquake magnitudes. Dominantly, this is related to the trailing seismicity piece of this. So you have to essentially put the brakes on an operation before your tolerance target to make sure that you're not going to actually reach this because of we're anticipating could happen after that. The other piece that's related to this is, so LPR is the only piece that has been put into Dutch law right now as the factor that must be considered to account for induced seismicity. If we take that approach and we only consider just this one single risk metric, then what we would expect is if we were stopping based on that, we would likely be encountering earthquakes that would have up to 1 to 2 orders of magnitude, either more nuisance or damage than what was already encountered at Hausinga, which was an earthquake that already ended almost an entire industry, certainly one of the biggest gas field in Western Europe. So that's probably not a good idea. For that part, I'll skip over that. But essentially, the second piece of the work, we've looked at how induced seismicity could be handled for EGS in the Netherlands. This was based on a calibration of tolerances from previous data, so trying to use lessons learned from induced seismicity in the past to hopefully avoid repeats of this sort of problem. And essentially then looked at and argued that multiple risk metrics are likely going to be important. So taking not just the local personal risk, but also looking at things like nuisance and damage to ensure that we don't encounter these sorts of repeat scenarios. With that, happy to chat if anyone has questions.
Thank you very much, Ryan. I will invite people to turn on their microphone, turn on their camera if they'd like, and join me in thanking Ryan for a great talk. Thank you. Yeah, and then a useful thing for us to operate with is at the bottom of your screen, there's a button that's called Reactions. And with that button, you can raise your hand to put ourselves in some order to have discussions. Hopefully easier. But yeah, I'll wait just a second until people may be ready to ask questions. So conceptualizing and thinking about what Ryan told us. And seeing no hands up, I will start the questions. Menadrine has got his hand up.
Yeah, I can't find the no hands up button.
Fire away, Menadrine. I will show you what the button looks like by raising my hand. I don't know, but yeah, Menadrine, you're up.
Ryan, you're a great talk. Thanks. You're touching on a point that I've always a bit puzzled about, and that's the connection between Bode's law, Gutenberg-Richter, and Omori. So basically, Gutenberg-Richter tells you that for every magnitude 5, you're going to get, in the long run, 10 4s. But Bode's law tells you that probably you're going to get maximum 1 4 for every 5. Now, how do you get that if you combine it with Omori? Is that just because you don't get to sample a high enough number, and so you don't get those other 9?
No, it's essentially just this relationship here. So this is more of the direct application to induced seismicity. So this is Van der Elst's largest magnitude here, which is related to magnitude completeness, the B value, and the number of events in the population, versus also this is just an inversion of the CDF for the distribution, where this piece is going to be, if you want to draw something new, a new Mmax value, you would just use some sort of uniform random value for the U here in this piece. If you're just taking this and combining something like that to get the difference between 2 samples, so this could be the stimulation phase and the trailing phase, or this can be the total amount of earthquakes and the aftershocks, number of aftershocks. In that piece, it ends up being based on this related to the B value piece in here, which is based on that Gutenberg-Richter piece, but then also the population ratio. So that population ratio, if you're assuming something in a Mori decay, just based on those parameters, you have then already a sense of, you have a sense of how many earthquakes, because you can also integrate this relationship, right? And get the total count of earthquakes, and then take that out to the limit of infinity for time on something like that. So that's essentially how that comes to be, or at least that's how people in the literature in the past for Both's law and making this probabilistic link to Mori's law and the Gutenberg-Richter relationship have linked these ideas, if that makes sense. But
Thanks.
Yeah, Ryan, it's really nice talk and a lot of things to think about. I guess one question I had was just, conceptually, how do you decide, how long to wait before you just, you say, well, this maximum trailing magnitude, especially in a multi stimulation case, then, how do you need some background seismicity right there or something to tell you how long you're going to have to wait for that trailing event, how big it should be?
yeah, that's a fair point. To be also fair, I guess this approach doesn't have any sort of time dependence in something like this. So this is essentially what I like about and why we designed this approach and determining the red lights is doing this in a way that's entirely source independent. So it's basically just saying, don't assume about anything about if the earthquake is going to happen or what those rates are going to look like. It's just saying, when would you need to stop, essentially, in something like this. And so this sort of piece of this equation here has no sort of time dependence in that. If you wanted to build on something like this and start incorporating real-time information, which is kind of getting into this plot here, this is just starting to build some sort of a bridge to that idea, where instead of because the first thing I presented, this solid line is going to be entirely time independent, and then now we're taking in some sort of time dependent or real-time information to update what that should be. You can then imagine the next piece after this would be to maybe do this in a fully Bayesian sense, where you would pull in the actual rate of seismic activity and then have some sort of forecast what that risk would look like. I guess also, so this is a long-winded way of saying I don't know the answer to what that question would be, to be totally frank with you, but it would have to be, I guess, looked into for how long you would have to wait. Because I haven't thought to answer that question yet, or it's not that I haven't thought. Some of the people at Skits also ask those very similar sorts of questions, which I wanted to answer, but I haven't had the time to answer yet.
Yeah. No, and is there an idea about how is there a predictive way to take the changes in RS that are occurring here and use those to tell you either how quickly to reduce your red light threshold, or is there some way to relate those changes in RS to the total volume that's been injected?
No, so that's I would be very excited if people took up that sort of work to try and put some sort of more physically predictive ways to look at what this RS could be. That would be, and then even get a sense of what it could be for particular like field sites or something like that. I've said nothing about that so far because I'm mostly been looking at this from an empirical perspective. But I think that would be amazing to have something like that. Because then that would give that would answer a lot of some of these questions about what it could be or how it could be forecasted. But that's all unknown.
Yeah. Others who are here, questions? raise your hand if you feel like it, or if you don't know how to raise your hand, just turn on your microphone and ask.
Hi, Ryan. Thanks for a nice presentation. This is Vikram here.
Hey.
I would have a quick question from this SFID test. I just wanted to know if you have considered any background information